This is quite a technical project. In theory, I'm a creative person, but it doesn't always feel like that. And I also love working with computers, and I also hate working with computers. And that's part of what feeds into this this project. So my background's in using Macs, but also programming in other languages, and then using them to do hopefully interesting creative things. So what is the idea? What are the design criteria? You may have read the kind of synopsis on the sheet, but I'm going to go through some of that stuff again. So I suppose my interest in sound manipulation is a lot to do with spectral and granular techniques. They tend to form the basis of the things that I've been interested in doing in a computer. Like with lots of things, I sort of, with programming in general, I sort of get involved in something and then I jump to the bit that I find the most engaging, which sometimes is also sort of complex and difficult to deal with. So what I've found in my experiences working with these kinds of processing is that I don't really feel that the tools that we have are particularly good. So the way that Max or SuperCollider typically represents audio is as a stream of samples, breaks those samples up into blocks. That's just for efficiency. If you're working in live, the underlying Ableton Live engine, the blocks are blocks of one sample, same in something like Reactor. But essentially, the idea is that the stream is infinite, or at least it starts when you turn it on and it stops when you turn it off, and there's no differentiation of time, and there's one sample per sample. And that's fine for all kinds of time-based processing, but it's a really ill-suited model for types of processing where we actually really need to deal with blocks of things, frames of things in one go. And I'll talk about some applications in which this allows us to do certain things, but the clearest one is spectral processing, where actually we have to gather a bunch of samples, transform them into the frequency domain, so we have to deal with a frame of samples. And the way that works in Max in the old days is horrible. The way it works now is with PFFT. I don't know what people have in SuperCollider, but everyone that I speak to says it's also pretty horrible there. And so what happens is that you're kind of shoehorning this kind of block-based model into a stream-based model. People don't make very many specific objects to deal with this stuff. And subsequently, I feel that what's happening in this kind of area is quite limited. So what I would like is something where I get frames of the audio that can overlap with one another, because with spectral processing, if we want to deconstruct sound and reconstruct it, we can't have the frames exactly back to back, because in order to window, we have to overlap. I'd really like it if these frames could be triggered at any time. I'll talk a bit more about that later. I'd really like it if I'm not fixed on some length. They can just be whatever length I want at any particular time. So arbitrary sized frames at arbitrary times. As I've mentioned, prior approaches are cumbersome. I think when I started programming in Max was about 2004. I spent 2 years working quite heavily in Max, and as part of that I was writing externals for PFFT, and I think the last time I did any spectral processing in Max was 2006 or something like that. I think I've spent about 10, except in teaching context, this is how you make this. I find it, so all of my spectral processing work really since then has been done in C++. And that's great, but it has all the problems of compiled languages. So it's slow. Okay, I've developed a sort of set of things that I could kind of plug together quite quickly now, but that takes quite a long time. And it's not good for rapid prototyping. So all of that stuff that you want in a creative language, the idea that you shove stuff together, you make something very quickly, you can try ideas out, that's out the window. But we can do some much more advanced stuff, so that's fun. So that's why I've been there doing it. But actually, interestingly, almost none of those projects have reached any kind of stage of completion. So I've got sort of two approaches, one of which I can't do the things I want, one of which I can do the things that I want, but you know, I have to worry about whether my machine's going to crash because I got some pointer calculation wrong or something like that. And the last thing to say here is that what I hear in this domain, and hopefully, if maybe you will agree with me by the end of the talk, what I hear in this domain of processing is often people sort of rolling out the similar kinds of things. So not really extending the practice of what's possible. And there are perhaps a few exceptions. So I should, of course, at least mention IRCAM's FTM project in Gabor, which is kind of one approach to this. Now, there are some specific design limitations there that I didn't like and that don't suit my way of working, which are again about ease of use. So there you have to take care of your own memory management. Everything's what you call in place, so you have a space in memory and then you operate on it. So if you send something from one object to the next object and then you operate it on again, the thing has changed, whereas the way that we're used to working in Max is, or a language like that, is if I send something in two directions, each of them maintains its own copy and I don't have to worry about it. Also, it doesn't operate. Gabor, which is the audio version of FTM, is a kind of hack to get audio processing running in the Max thread, and there are various limitations of that to do with multi-threading and so on. So there is a kind of precedent there that allows some of these things and starts to get into more cutting-edge technologies like doing additive synthesis based on FFT analysis or something like that. But there are a lot of other things which haven't really come into usage. So where is this heading? So there's no language I'm aware of in which it's relatively straightforward to put together multi-resolution spectral processing. So in some way combating this time-frequency resolution. If you process different parts of the spectrum using different FFT sizes, it costs more, but you can potentially have better time location in your high frequencies where you care, less good time resolution in your low frequencies where you don't care. This is the approach taken in isotopes RX or something like that. It exists in the commercial world, can't build it easily. There are some advanced techniques. Multi-taper spectral analysis is a technique used in things like geophysics. I was just looking before I gave the talk about when the first paper on that was. I think it's 1982, which is before my birth. But no one is doing that in the musical domain, again, except perhaps within closed projects, because people don't know about it, they don't know what it does and how it might be useful. Things like descriptor analysis that I've worked on before, just simply zero padding your FFT analysis. In Max, you have to know a whole bunch of stuff that's undocumented. It is possible, but you have to make your own window, and you have to know that the window is actually, you should zero pad at either end rather than at the end for various reasons that I won't get into now. What about things like wavelets or sinusoidal representations or other transforms? None of this is accessible. Every so often someone kind of makes an object and then it disappears and no one uses it. Granular synthesis. Okay, a lot of the time in Max I've done some work on how to make granular synthesis with really accurate timing, but you're kind of working around the language. So what about a language or a way of working which that's built in? The grain is really a unit. Now, there are some downsides to that I'll talk about later, but sometimes I'd like to do stuff where I know the whole contents of a grain and I can operate on it as a grain, which again doesn't fit within the stream-based model. The stream-based model gives us efficiency in a certain way, but it would be nice if I could just get the whole thing, do what I want to do with it, and be done. Also, I have to do things like voice management. Actually, we'll see later in FrameLib, if you're doing granular stuff, there's no such thing as voice management. You just paste grains into your output, and that's how it works. Things like content-aware processing or very finely timed DSP, which you can now do to some extent in Gen, but this is another kind of a way of thinking about it. And things like musical gesture sort of generation that might come in sort of later on. So this is my kind of wish list. What are my design criteria? So this is got to be something that works in real time. As I said before, arbitrary rate frames, arbitrary size frames. I want it to be lightweight, so I don't want it to involve too much learning from someone. Ideally, environment agnostic. This actually came from a grant proposal that I put in with PA that was unsuccessful, and it started me thinking about the idea of writing code that would start out not in a particular environment and then be bound to an environment to make it more portable. I'd like it to be fast. I said ish, that's not actually been a concentration so far, but it will be later on. And I'd like it to be extensible, so I'd like it so that if I want to add something to it or someone else wants to add something to it, they can do so. Now I've split this into two halves because of this extensible part. What about people who are using it? And when I say user experience, I don't mean user in terms of end user, I mean someone who's programming with it in an environment like Max. So they're not developing for it. So ideally the representation of processes will be relatively simple, bearing in mind that some of the things that I want to do are complex in and of themselves. Flexible representation of data, minimal setup. They want to think about their processing, their creative tasks. They don't want to think about technical concerns. And they don't want to have developer level concerns. That's for developers. So in a way, what I've done is these things that I want to happen, I have all put off by doing some very technical things. So some of the work for this project has been very low level, looking at things like memory management from a relatively low level perspective, in order that hopefully later down the line I and other people can forget about those things to have a better sort of creative workflow. If someone wants to come and write an object for the FrameLib, I want them to write the minimal amount of code possible, and I'd ideally like them to have to not engage with things that might be sort of unsafe, or protect them from making errors as far as possible, and make it straightforward for them to code. I've added 3 objects since Thursday, starting at about 5 p.m, in order to make what I hope is the best demo today. And bear in mind I've been at concerts and other things, so hopefully it is relatively fast, and maybe I'll show some code and show that it's relatively short. Okay, just 2 things to talk about before we look at the system. There's more to it than this, but the 2 things that really stuck out was, one is about I'm building kind of a DSP network within a DSP network, and there were some thoughts about how that should work. So typically, again, we would split, so one approach is to split a network and serialize it into, if we process this object and then this object and so on, so you traverse the network, you figure out a valid order, and you process in that order. That at least used to be how Max works. I think it's still how it works, but I'm not 100% on that, because they can change those kinds of things without notice. In FrameLib, I take a different approach, which is a bit like the approach taken in, I think, some Faust code, which is about dependency counting. So essentially, each object has inputs and outputs, and you look at the inputs and say, are the inputs ready? Is the output ready to accept a new input? So, and if all of those conditions are true, then you can process that object. What that allows me to do is actually there's no traversal of the network. There's a totally distributed system, so the objects know what they're connected to, and that's more or less it. It's slightly more complicated than that for another feature, but for the basic underlying network, they just know what they're connected to, and then everything can be processed in time. In fact, the queue that they have to process is actually built into the object, so they're just pointing at each other, and it just works its way through the queue. And it's a kind of push-pull model, which means that sometimes the inputs are ready, so it pushes through the network, and sometimes the output gets freed up and it then pulls output through, so it can push and pull in both directions, which means that the algorithm always advances, it's non-blocking. And because the key idea is really about time in the network, because I wanted this thing a very accurate timing, so each object is moving forward in time. And actually a lot of the underlying code is about calculating which frames are arriving together, which frames are arriving asynchronously, and dealing with that. That's all dealt with for you, and then you get a call in your object that says, okay, the input's all ready, do something. The nice thing about this approach is that it's inherently multi-threadable, because it's distributed and we don't have a fixed serial order in which we need to do things. All we need to do is know, is it ready to happen? And then if 2 things are both ready to happen, we don't care about the order in which they happen. Just we process one or the other. Now, it's not yet multi-threaded, because a couple of parts of the system need to be developed to do that. So the queue system needs to be multi-threadable, and the memory management needs to be multi-threadable, which right now it's not right down to the bottom. So that was a key kind of part of the work, because this kind of idea of scheduling and scheduling of time, and particularly this thing I wanted, it wasn't there as a kind of particular initial concern, but because I wanted things to be able to arrive at any time, I also didn't want to be stuck to having one clock driving the whole network. So you can actually have 2 different clocks pushing data in at different times, and it will kind of resolve that. So that's also something that's been sort of interesting to me, the idea that you might want to run control data at a certain rate, something that's quite expensive, and you might want to run something else at a higher rate, or you might want to update something only when the user does something. You don't want to update it at a regular rate, and in FrameLib that's all possible. Second kind of big, I'm just talking about two of the core features, big kind of task has been memory management. So to my mind, you don't want to worry as a user, as a programmer of FrameLib, or even as a developer really, about how that is being handled. It's got to be real time, so we want something fast. So ideally that would be a big O complexity of 1, so fixed complexity, which is not the case if you're calling like a system routine like malloc or something like that. For audio systems, it's also really good if we're using memory just to store the inputs and outputs, to reuse them frequently, because the cache reusage on your computer will be faster. It won't be loading things in and out of memory. That means the code will run faster. Again, that's a very technical concern that someone needs to worry about, but it shouldn't be you, or it shouldn't be me later, let's say. So currently what happens is that I have an underlying kind of algorithm called a two-level segregated fit, which is one of the only times in my life I've managed to not write my own code for something, although I did find that I needed to modify it, so I couldn't quite keep my hands off it, but that seemed a little bit too technical to write a memory management algorithm from scratch. And that's an algorithm that's designed for real time. So given an initial pool of memory, it can allocate and deallocate that memory in a fixed time, which means that it's fast. And you don't have a situation where you need some memory and suddenly have to wait a much longer period of time, which can happen with system allocators. Now, it's not possible to work totally within that because I don't have the whole of the system's memory available to me, and it would be kind of rather sort of not good practice to allocate some huge pool of memory at the beginning. So what I do is I have a secondary system that starts with a pool of memory and adds bits to it and takes them away. So it's constantly monitoring how much memory is in use and whether it needs more. And calls to that secondary system-based allocator in secondary threads, with the idea that hopefully should be less obtrusive to the audio threading. That stuff got finished about 2 months ago. I haven't really had time to kind of test it for speed, but it definitely at least works. So it should be able to grow and shrink as you need it. The other thing is you don't want to have to worry about, okay, if I've said that data can come in at different times, I don't want to just leave all my inputs and my outputs are changing size all the time. I don't just want to leave memory lying around. So the system also takes care of when it's not going to need an output to do a calculation anymore. So if you've got a chain of objects that just go one to the next, it actually knows that once it's done that calculation and it's gone into the next object, it can free that memory up. So it should be dynamic with no effort on your part. There will be a few situations in which potentially it could be more efficient, but I've tried as far as possible to have it deal with that in an efficient way without you having to think about it. So those were kind of two big design problems. I want to get into looking at what it is and then seeing it in action. So the result of all this thinking is an extensible library of C++ classes for real-time frame-based processing. You have this idea of a scheduler, which is something that triggers other objects to process. So at the moment there's only one of them, and it's called interval, and it just sends a trigger message at an interval of so many samples. I think you can probably do it in other units of time. I can't remember if I've put that in yet. And it's quite minimal requirements on the host environment. The host environment needs to process audio in blocks. They could change size. It just needs to process all its objects in one kind of pass with the same block size each time. Across all the objects, but between calls they could change. So there's kind of three components to this. The first is the kind of framework, which is kind of underlying stuff. Second is environment-specific wrappers, which right now there's just one for Macs, which is a set of code that just binds it and allows you to load these classes as objects, Macs objects, and to patch them together in a way that looks like normal Macs objects, but it's sort of not exactly that under the hood. And then finally, a set of objects that deal with specific DSP tasks. Right now there's about 90, which sounds like a lot, but they're not all kind of handwritten. Some of them are templates. So this is what we have. We have a framework which deals with scheduling, processing, and audio processing classes, real-time memory management, high accuracy timing format, so actually it deals with samples, not just samples. There's a kind of multi-channel expansion, so we can actually, and this is partly for multi-channel, but it's actually more for cases like, let's say you have a multi-resolution FFT. I've written my processing chain. It'd be really nice if I could just pack together all my different resolutions, push them through the same processing chain, and then separate out at the end, so I'm not having to copy all my code. So the way that works is you kind of literally pack them together, you put them through one chain, and that chain then automatically expands out to do parallel processing. And there's a bunch of uses that you might use that for, so it's called multi-channel, but it doesn't necessarily mean channels in terms of output channels. There's some templates to make it really easy to write just an operator that takes two numbers and does something to them, or takes one number and does something to it. There's, as I say, the environment-specific wrappers, and then the object library, which covers some basic maths, some vector type operations like what's the maximum value in this frame, or what's the sum of this frame, or what's its mean value. Some simple scheduling objects, things like to do with scaling and control. Just a few specific spectral processing objects, and we'll look at them in a minute. There's a few filters that I just hacked in there quickly to do some interesting stuff, and a few kind of miscellaneous objects, things that I needed. I haven't actually spent that much time writing objects. It sounds like I have because there are 90 objects, but actually most of the object development has been quite fast, and just to have some stuff to work with. And it's kind of at the point where you can do real stuff with it, but some of those objects will still change as I kind of clean them up. But let's just look at a kind of example. I said earlier that it should be relatively easy to write an object. Here's an object called count that just takes a frame and input. Well, there's two ways it can work. It can either take just a trigger and it creates a frame which is just a count from 0 to the length of the frame, or it can take an input and then it just creates an output of the same length, counting 0 to something. So the core part is this process routine. There's a little bit of setup and a little bit of an update, but to write an object like that is sort of under 100 lines of code. It's relatively straightforward. Once I start adding kind of documentation, it might get a little bit longer, but it should be quicker than even writing a standard kind of max object. And I tend to get quite annoyed when I go over sort of 100 lines or so, which I have done with a couple of them. So I'm going to show you later an object called multi-taper, which is 180 lines of code. I'm quite annoyed that that's so long. I wish it was shorter, but that's actually really mostly just the core. You'll see there's a bit of memory management stuff. Most of it are these core loops that actually do the thing, so I can't make it more efficient than that. So there's very little kind of boilerplate code that you have to write just to get stuff up and running. Okay, so that's a lot of introduction. Let's look at some actual code somewhere. We don't need that. We probably don't need that. Oh, they're already there. Super exciting patch that we're going to start with. We'll start with this music. So what's going on here? On the right hand side you will see a delay tilde object that's delaying the sound by 1,000 samples. On this side we've got a source object which is just chopping the audio up into frames. Right now every 1,000 samples it gives me 1,000 samples. So I have a latency of 1,000 samples in order to chop that up. So the idea is that and then the sync is just pasting that back into max land. So here I'm in FrameLib land, and here I'm in standard max land, and we hear that the same sound comes out of both speakers. So this is just my demo cable patch that proves that it does something.
You throw down the blanket, say let's sit here for a while, I'll find a way to open this wine. The fisherman is silhouetted by the arm.
So we should see that if I don't retrieve frames as often as I should, I can hear the kind of choppiness of the output. If I retrieve them twice as often, that speaker gets louder because I'm doubling the amount of samples, all still with the same latency. So as you can see, it's really exciting. That's why I spent sort of months. I think I started this project, the first version of this project I started in 2008. This one I started slightly more recently in about 2013. So you can imagine how pleased I am to be at that stage. It's okay, it gets a little bit better than that. I haven't opened all the... yeah. it'll be fine. There might be a crash later, but that'll just be exciting. Cool, okay, that's a granulator, a granular synthesis machine, based on the Jungly sample. It's not my favourite. Cherokee is my favourite, as all my students know, but I'm using Jungly here just for sort of historical reasons. So what am I doing here? Every 100 samples, I create a count of 10,000 samples. I get a random number of a length, vector actually, with a length of 1. I multiply that by 1,000 and I add the two together. So, over here I'm doing a sample rate conversion into milliseconds. So what I've done here is I've created a ramp which goes from 0 to 10,000 samples, but in milliseconds. And then I add a random offset of up to a second to that. Here's a read object that reads out of a buffer. Just for fun, I put a one-pole filter in there. Then we window the output, and then I paste it into the output. So hopefully, that's what's good about this demo is it shows that there's not very many objects on the screen. This would take me quite a bit longer to do in Max. I'd have to worry about voice management. I'd have to tell my voices when I was on and off and all this sort of thing. And we've got to this result quite quickly. With an added filter, which we probably wouldn't have bothered with in our Max example. Okay, so that's a quick demo just to sort of show the ease of things. Let's make something. They just don't fit on the screen. This is a slightly more fully featured example. Here, I'm running about 300 grains on top of one another at a time. I've just added a few extra things. So if we look at the bottom, I've got panning. So it's just a simple cosine based panning. So I'm taking a cosine or a sine value. The nice thing about the things like the times object is by default they do what's called wrapping. So if I put one value in the right and a whole bunch of values in the left, it will multiply that all of them by the same value. So although the cosine operation is expensive, if I was doing this in MSP land, I'd be calculating every sample. Here, I'm only generating it once per grain. Again, a window, slightly different window this time. Slightly better filter, which I think I ripped out of some of Ollie's code implementation of someone else's zero delay SVF filter. This looks very much like our sample reading before. And what we see at the top is just a bunch of random generators for different parameters. So I'm actually changing the length of the each grain. I'm changing the offset of each grain, changing the frequency of the filter, which is giving us this nice liquid sound, and this will be for the panning, which is being mapped onto half pi. I need to make an object to make nice constants, so I was thinking about that this morning, just because my cosine and sine are running in radians. So again, haven't had to make any, even do any sub patches or anything like that, and okay, and I'm getting about 40% for about 300 grains, which is okay. It's not bad. I'll live with that. So far we've seen things that we could make in Max, but might take us a little bit longer. So we've seen some of the kind of ease of use. I'm going to show a couple of other examples. We'll move towards looking probably for quite a while at the spectral dynamics patch, what I wrote this week. And we might look at these in a slightly different order, actually. Here's a nice example of something that you probably couldn't easily do. Again, you could do it, but it would be a pain. Here what I'm doing is I've got another granular synthesis thing, but I'm reading from two different samples, Jungly and Cello, F2. I'm windowing each of them, and then I've got an object which I made based on some of the kind of histool stuff which I previously released, and it takes two time domain signals and convolves them against one another. So it does actually convert them into the frequency domain, but it takes just one FFT and convolves them. So what I'm doing here is I've got a granular synthesis patch in which I have two grains convolved against one another rather than just one grain. You could build this using the histool stuff in Max, but you'd have to do some calculations again. I'm going to convolve the IR of this length against a grain of this length, so when am I actually done? Stuff that I don't care about. What I'm thinking about is give me two grains, convolve them together, that's my output. This might be overly loud. I think I changed it so it wasn't a silly... No, it looks like I have. Yeah. There we go. So, if you'd wondered what that would sound like, that's your cello F2 sample against jungling. We can vaguely hear more of the cello F2 sample and vaguely hear that kind of rhythmic pulsing jungling. So that's kind of moving into the territory of stuff that would be quite a pain. Let's look now at some spectral processing. I'll probably just show this gate just because it's nice and easy. So the process here is grab some samples, put them through a window, take the FFT, do some stuff, let's ignore that, take the inverse FFT, window them, and put them to the output. And as I've noted there, I need to sort out some amplitude scaling. It doesn't work right, and I can fix it, but I just haven't got around to figuring out which of the windows should be compensated in certain ways. That's one of the things actually that I'd like to add. I think that it's actually quite, it shouldn't be specialist knowledge, but people are actually quite unsure about, how do amplitudes within a PFFT work, and part of that's to do with what they have compensated and what they haven't, and in certain ways. So if I take an FFT of a 0 dB sine wave, generally the level inside after I've taken the FFT, if it's exactly on a bin, will be the FFT size. So it won't be -1 to 1 anymore. The amplitudes will go from 0 to the FFT size. But my windowing applies some gain, and depending on whether that's compensated, I need to know something else. So some of the things that I'm going to add into the FrameLib are just very simple things, like being able to do normalized FFTs, so they always go 0 to 1, so you can set your thresholds and things like that sensibly, correctly compensating window gains in the right place, so you don't have to know what the gain of your window is. These things are kind of, again, extra knowledge that someone needs to care about, but probably not musicians. So what am I doing over here? I'm just taking the hypotenuse, or doing Pythagoras, to figure out the amplitude of each bin. Threshold it, is it greater than some number? Over here, I'm just bringing some numbers from the max land, so I'm polling them at the frame rate. And this is just some maths that kind of tilts the threshold over the spectrum, because you'll hear that if I leave it flat, we'll just tend to get more with the spectral gate from the lower frequencies because they tend to be louder. So I've just made a simple tilt function that helps me with this. We'll leave that for later, we'll go here. So turn my audio on. Is my audio on? I can't see. No. It's like a great YouTube video. It's got that nice grainy quality. So my tilt's kind of the wrong way around. Minus numbers are tilting it towards lower on the high frequencies. Well, that's the way around it is. We could think of it either way. I can also tilt it the other way, which is less useful. But the idea here is really to show you that, again, stuff that PFFT gives you, which is this, is quite easy to put together. Then you put your processing here. I don't have to write another patch. I don't have to save in an abstraction. And again, slow my workflow down. Obviously, I can sub-patch as I like, but I can work in a sort of normal environment. Okay, so that's got us to the point that we've seen that I can do some spectral processing. Let's look at some things that don't exist within Max. So this is a simple example where I've made an object. Now, this is still at the level of stuff I could make for Max, and there will be some other examples like that today where you could say, okay, I could make an external for Max, but firstly, that would only run in that environment. Secondly, some of the kind of ways round, thinking round things are kind of conceptually not how I want to arrange them. So here what I'm doing is a median filter. So I take my amplitudes as a block, which within PFFT I do actually, they have actually organised things in PFFT, so you receive all the stuff together. So if you do write an external, you can deal with blocks, but that's the only way. But you can't do something like deal with blocks of different lengths at the same time. So I take it as a block, and for each bin, I go before and after it by a certain number of bins, and I take the median value. So each value becomes an average based on a median around its value. This is useful for seeing, then I can make a comparison to the value in the bin. That's what's happening here, the less than. If my signal is peaky, then the median will be lower than the peak. So if it looks like a sine wave, which tends to look like a peak in the spectrum, then it will be above. If it's noisy and the energy is spread across several bins, it will probably be below. So this is a technique that allows us to separate out quite simply noise and transients on the one hand and sinusoidal content on the other. So this is getting towards the sort of techniques that I think we should be able to approach in 2017, but that people aren't necessarily aware of or using in the kind of more musical community. In the more engineering-based community, these are things that people know about. It's not that I'm inventing them, it's that they haven't necessarily been translated across. So right now we're listening to both. This bottom part is just a selector that selects either both signals. So I'm actually just using this power object to create a vector of ones, because when I wrote this patch there was no other easy way to do that. So anything to the power of 0 is 1. So I'm multiplying, I'm using that at the moment, and then I'm going to switch between the sinusoidal content and the noise-based content. So we should hear our transients disappear. What's coming out the other side? So that's the kind of transients of the guitar sound. So that's using median filtering to do a simple kind of separation. We could improve on that probably, but this is just a kind of demo. Actually, it was inspired. I went to a talk in the APL and Steve Fenton was doing this for some of his analysis work, and I was impressed by how good the separation was for such a seemingly straightforward technique. You're not looking forward or back in terms of frames, so I thought, great, I need to implement that. Let's look at some code that's something like I might write in Max. So we're actually going to look at some bad code, and then I'm going to spend a bit of time trying to make it sound a bit better. So this is a spectral compressor. You can trust me on that. It looks a bit complicated in terms of dividing the powers, but this is just one way of setting an amplitude in a linear domain, creating a ratio. It's a totally hard knee compressor. The minimum at the bottom means that the compressor can only push downwards, otherwise it would actually compress underneath the threshold as well. If I change this to a maximum object, I can make an upward compressor, so I can actually switch the modes if I want. But basically, there's in its default mode, there's no smoothing. There is a smoother here, but I'm going to leave it at 0. And it works per bin. So this is a kind of spectral compressor that I might talk about in my second year module. And we're going to hear how good it sounds or otherwise. So right now it's not doing anything. The ratio is set to 1. So if you think, oh, that doesn't sound good, then you don't like Peter Gabriel's mix, which I think is quite good, or whoever did his mix. So let's start engaging it in some way. I'm going to put the amplitude higher. 1 is not the top of the range. It's actually really far down. I'm going to pull it back here in a minute, but let's say it's something a bit higher. Tracks, you could have an airplane flying if you bring your blue sky back. All you do is call. Okay, we can hear it start crunching down on certain frequencies. I've got a stupidly high ratio of 11 or 12. I'm now going to pull it right back to 1, and we're going to hear how bad this processing sounds. Right, what's going on there? Why does that sound so terrible compared to our expectations of a compressor? It's not just because it's pulling up all the noisy components. It's actually because it's treating every bin separately. So when we put a single sine wave into an FFT, we don't get a single output bin. We get a spread of energy. And some of that energy is what we call sideband. So it's actually energy that belongs to the main sine wave. And we're treating it like separate information. So those sidebands are being boosted to the point that they're really loud. And this is why we get this horrible kind of distortion type artifact, because essentially what we're doing is we are destroying the kind of frequency, the important frequency and temporal characteristics of the sound. Bear in mind this is probably at like minus 50 or something dB. Because of all the amplitude scaling issues, I can't tell exactly where it is right now. Let's smooth that a bit and it's going to get a bit better. Okay, if we smooth it a lot, and I'm smoothing the same in both directions, it sort of becomes usable, but that sort of graininess in the sound is still there. So I've got a second patch which is a bit more flexible. Everything's hidden away nicely in this detector code. You'll notice that nothing out here has changed. It's the same thing, just some multipliers. Let's have a quick listen to that without turning any of the smoothing on. And then let's talk about why it sounds different, and then we'll also add the smoothing in. It also sounds bad, so if you're thinking that doesn't sound that much better, I do know that. But let's compare it back to our no smoothing on this one. There's an improvement. It's not perfect, but there's an improvement. So what's going on? Several things. So here's my kind of detector code. I've only hidden one bit of it away because it was, let's unpin that. See if we can fit the whole thing. And okay, we don't need to worry too much about that storage. So what's going on here? Firstly, I've added this object called multi-taper. So I'm actually doing my analysis of the original time domain audio. So I brought time domain audio in along with my frequency. And the multi-taper is essentially equivalent. It's a faster version of doing this. It's equivalent of taking several different windows, actually some of which go negative, and calculating the power spectrum on all of them and averaging them together. And that allows us to more effectively use the data. The power spectrum of one FFT frame is actually really biased, and we can have a massive variance. So actually, our initial representation of power spectrum, what the power is in different bins, is bad for a start. So our spectral dynamics are never going to sound that good. So I'm starting with that, which gives me a power output, so I have to square root it. I'm also then detecting peaks. So I'm trying to detect bins that are peak values and then go to the minimums near them. And this is actually giving me an index for which peak is in which bin, or for each bin, which peak does it relate to, what's its frequency, and what's its amplitude. And they've been corrected based on the three nearest points, so they've been parabolically interpolated. So again, they should be better estimates of what the components are, because we know if a sine wave is exactly on a bin, it will give us a nice high amplitude. If it's halfway between two bins, that amplitude will be split between the two bins. So again, if we want to get a realistic estimate of what the amplitude is, we need to do something a bit different. This isn't running at the moment. I'm just bringing in fixed thresholds. We'll come back to that in a minute. That's exactly the same as the detector we saw before. Beneath that, I have some smoothing, which is kind of the same as the other one. The nice thing here is that I can actually recall what the last set of outputs are, and then I can store them over here in a controlled manner. I can actually smooth between two different points in the network. So whereas in MSP land this would be a vectoral object, here I've actually built it from core objects. Over here, the last bit of this lookup stuff, so what I'm doing here with the lookups is for each bin I'm actually outputting the amplitude of the relevant peak. I could actually run this detector on, I left the other amplitude input, but I could actually run this detector on the peak values, which would mean that it would only run for, let's say, 200 peaks per frame rather than every single bin, which would also make it more efficient because I can change frame size. So these frames are much smaller and changing in size than this frame. And down here, I'm actually looking up, I'm using the frequencies, rounding the frequencies to the nearest bin, and I'm looking up the amplitude change that would be applied to the peak bin. So the amplitude change is actually flat across all the bins in one peak, rather than being applied to each bin based on a separate value, which again is one technique that we might think about using to keep our peaks kind of roughly together. So if I start adding smoothing to this, which actually works much better as a post-smoothing than in the other patch, I can actually get some really fairly good results. Okay, so now I've actually got something that's of the sort of audio quality that I might actually think about using, rather than kind of straight out of Mac's kind of spectral processing. I'm just going to edit this code, hopefully without crashes, to set my thresholds per bin. Sorry, not per bin. This is actually another nice example where I'm putting these into a buffer, as you might do in Macs, but when I read them, again, because I can read frames in a variety of ways, I actually create a count that's my bin size. I map those logarithmically onto, and then I read them out of the buffer interpolated. So I'm able to use a small number of, I think 30 sliders here in a logarithmic way, so a more meaningful way to control the thresholds. That's the only thing. I could make any of these dynamic by frequency. So it might seem a bit like it's an EQ. That's because I'm crunching down so hard on the parts of the spectrum where the thresholds are low. Let's do the opposite. Or actually, let's make it into an expander. Yeah, if I can make it into an expander by taking the ratio beneath 1, that's right. So I'm going to sort of... Could have a So that's actually an upward expander that can get louder. So the idea here really is to sort of demonstrate that some of these techniques that I would be using in my C++ code of looking at spectral peaks rather than looking at individual bins, looking at things like multi-taper analysis, being able to actually interchange, we don't have to be so picky about keeping data together that relates to the same thing, but the frames are different sizes. So here I have, as I say, these peak frames that show me where my peaks are located, which are a different size to my actual spectral frame, which in this case is half the FFT size plus 1, because I keep the Nyquist bin as a separate bin. And how we can actually move, let's, if we go back to our kind of original spectral compressor, if I still have it up, and I'll set it to something a bit more sensible. And turn audio back on. So even on these settings with no smoothing, we really hear the graininess. And post-smoothing actually in this case doesn't work very well because of the way that it works a little bit better if you pre-smooth it. And then let's move to this kind of spectral dynamics. I'll set it back up as a compressor again on similar kind of values. So what was that? A ratio of 4, and I don't know where 12 is. Let's flick it back onto here. Just make sure that the DSP is recompiled. So even with no smoothing, we hear that it's much higher quality sound. And with temporal smoothing, we get really quite good results. That's probably enough. I do have another example, but I want to leave time for questions. So thank you for listening. Yes, I have one more slide that I'd forgotten about, which is in here somewhere. So yes, the question is, what's the to-do list? So I'd quite like to get multi-threading DSP and connections. If the connections were also multi-threadable, it would be quite a good environment for live coding, because you'd be able to connect things without breaking the network. But that's very much like a nice to have. Multi-threading the DSP is kind of more where I'm at. Possibly thinking about a non-real-time equivalent, so you can do stuff kind of offline and push it in. I don't know if that's the right way to go there. That might be a different project that just communicates with it. I'd like to complete the basic object set, make more of these kind of advanced spectral tools which start to actually realise this dream of bringing more advanced processing to other people. The only documentation right now is the C++ code, so that's good for me but bad for everyone else. So I think that Frederic and I might work together on making that happen. And then, yes, I'd quite like to write a Super Collider wrapper, possibly before public release, although there are a few issues that I have there. I made a few, maybe not mistakes, but a few things which are, the design of the underlying objects is not Max-like, but whether they'll fit into a kind of Super Collider type style is a bit debatable. It might be a bit more complicated than that. It might involve some kind of scripting kind of thing that runs within Super Collider, but I've still got to figure that out. So yes, that's what's coming next. Thanks. Questions? Yeah.
It seems to me that there's some matrix input missing on the granular.
When you say matrix input, what do you mean?
I mean, basically, it would be cool to be able to use jitter matrix to control grain parameters.
Yeah, that would be my guess. To write that object. So the only thing there is that actually communication between Max and the object is a little bit complicated. Right now you'll see an object called from Max, and that kind of takes in data and then it stores it until it receives a trigger in the FrameLib land. And the reason for that is, rather than make it really easy, like you can just plug things in, I really wanted to make people think about when things are happening. So all the time you have to control when things happen. So I mean, I guess that could just work in the same way with jitter matrices, actually. So yeah, I don't know why I'm thinking it's different, but yeah, you kind of have to take it in, store it, and then once it's there, have something trigger it going into. At the moment, the data, I should have said, the data representation is just a vector of samples, so you only have one dimension. That's not, it's quite embedded in a few places, but actually the underlying scheduling doesn't require that. The data could be anything. There's a secondary data type. I haven't really talked about parameters, but there are things called parameters which happen only once per frame. And you can actually send a whole bunch of those in one frame, sort of serialized together. So in theory, there could be more data types, and certainly FTM has a vector and a matrix, but I just kind of thought most real-time stuff doesn't require matrix-based processing. Let's see how far we can get, but yeah. Any other questions? Yes?
When is it going to be released?
When is it going to be released? That's a very good question. I have this thing called a sabbatical coming up in July, and also the deadline for ICMC papers is at the end of
April.
March.
Is it March?
I believe so. It's on my board, March the 28th, which is in about 4 weeks' time. So it's kind of good to have a paper, and it's kind of a bit naff to have a paper and then say, oh, the software's coming. So I did want to run it for a year in beta with a small number of and I have actually used a small number of people to ask questions about, like, what should this look like. So yeah, it'd be really nice if it was public in a year in some version. But in terms of people using it before that, there's also possibilities there. It's just, you know, I want to kind of send it to people in a version where it's like, if you make something with it, it's not going to totally break, but at the same time, at the moment, it's like, if I send this to you, that object might change a bit. Mm-hmm. So there were some key things. So actually, one of the reasons I didn't go public a year ago is that you had to put all these cables between all your audio objects, the ones that were going to talk to Max, to tell it which order they had to happen in. And actually it turned out, and I solved that problem in the summer, so actually the ones that have audio connections actually have a secret patch inside of them that's secretly connected to another object that I found somehow, and that was a lot of fun. But I knew I was going to do that, so I knew those connections were going to disappear, which would mean that all the patches that I'd written previously had to be repatched. So now I've done that, I'm kind of ready potentially for it to go to people. So if you'd like to try it before then, there's a possibility there.
How does the multi-channel
Oh yeah, do you want to see it?
Stereo patch, but make that multi-channel if there's like a shortcut.
Let's look at one. I haven't run this in a while, so let's assume that it works. Let's see if it does something. It's definitely my favourite. This one's normalised, I think, this threshold. Now, you may be able to hear, if I get it low enough, that the gating's much quicker at the top end than the bottom end. So what am I doing here? Here's my gate code. Here's my multi-resolution in. So my multi-resolution in is a bunch of intervals all running at twice as fast as one another, or something. Yes, and then taking half the size. And then I use this pack object to just pack 4 of them together. I shove them through my network, and at the other end, I unpack the results, and then I delay them to realign them, and then I filter them. I'm not going to show you those filters because that probably looks really horrible, and it's not a particularly efficient filter. It's quite high quality, but just for the demo purposes, even though the demo doesn't sound particularly good. So that's basically what you would do. You would just shove stuff together, then shove it through a network. If something is coming in from here, which has only got one frame, again it will wrap them against one another. So you can do, I have a granular patch which I haven't shown today, which does descriptor analysis on each grain and spatializes based on that. I partly haven't shown it because I think the other one is more audible, partly because that works really well in multi-channel and stereo. It's not quite so impressive. And there, what I do is I actually use multiple channels for each of the speakers. But so you have like however many speakers you've got, 24 just packed together. The coefficients, which are very small vectors of one number, and then I multiply them against just one vector, and that splits out so you get 24 outputs, and then you unpack them again. So you can do some quite clever stuff where you combine different numbers of channels and it just does something vaguely sensible, I hope.
In the patch where you had something stereo, I can't remember which one it was.
Yes.
Stereo.
Here I'm not, okay. Yeah, let's...
So you've got 2 FL sync.
Yeah, so at the moment my sync object is mono, so you have to have 2 syncs, but let me show you how that works here. So what I could do is I'll get rid of this because it's in the way. Ugh. I could get rid of this times object. I could add these 2 together, do my multiplying in one object. There's not very much point in doing it here, but this will work in theory. I haven't done any multi-channel stuff for a while, so if it doesn't work, it's not my fault. There we go. So that's an example of a quick sort of multi-channel expansion where I create one grain and then I multiply it against 2 different things or something like that. So, and you can imagine, yeah, as I say, you can make those splits wherever you want, and wherever 2 things kind of come into contact with one another, it will modulo the lower one out, the lowest ones out against the highest ones. So you always have channels to deal with. So it always expands up to the maximum channel count. That is non-dynamic though. That's one of the things that is fixed. You have to say how many channels there are. Although actually, so you don't have to say how many channels there are. You have to, but there will be a fixed number of channels. But if I have 1 channel signal coming in here and a 7 channel signal coming in here, what will go out will be an 8 channel signal as well. So the pack object just puts things together. And in fact, I think if I put 3 here and I've got a 1 as it, and then I don't connect anything and I put 7, I still just get 8 channels out. It's just to sort of solve various problems of what would happen otherwise, or stopping you from having, you can't like pack hierarchically, which would kind of be nice but really complicated. So you just have, when you pack channels together, you're just adding them together in a kind of bunch, and then when you get to the other end, you just unfan them. But there will probably be a version of the sync object at some point, which automatically, there'll be a mode you can put it in, where it has multiple audio outs and you can just put one in because this is an obvious thing to do. I just haven't figured out quite how to make that happen yet. Okay.
What's with the hash sign?
Yeah, well, okay. What's with the hash sign? What's with the hash sign is that these are the parameters that I was talking about, which I'm going to definitely call parameters now, not attributes, which is what they're called in my code. The reason for the hash sign is that the @ sign is a max attribute, and if I could use that symbol, but it would encourage people to think that they could use normal max messages, and you can't. And one of my questions, I don't know if I have, I might have the email, or I might have the, I don't appear to have it, but somewhere I have a, there we go. This was a patch that I sent to a bunch of people, and I said, which one of these should I use? And everyone gave me a different answer. So I quite like some of these with the square brackets, and I don't like these ones because they look really like C programming. So I did all of the characters that I thought would be available on a sort of standardish keyboard without doing really crazy key combos. And so if you want to put your votes in, then contact me, I'll send you this patch. So there's two things you can do. You can set parameters. You can also set inputs. So I can actually, if at the moment I've got this kind of hack so that if you put one number in a binary object, it will actually be sent to both inputs. So it behaves in a max-like way. That's done at the max wrapper. But there's actually a facility for inputs to be fixed. So there's a facility for you to actually store a vector of numbers in a times object or something like that. So that's what these syntaxes are. So I would be interested in people's input on that, because again, once I make that decision and release it to people, I have to stick with it, and it would be nice if it was something that looked nice. But yes, unfortunately, all the people I sent it to said slightly different things. Some people like the hash. It's not my favourite, but
You could put a question mark.
question mark. I think, yeah, I didn't do that one, did I?
No, you didn't.
I'll think about that, yeah.